that the audio is working. Hello. Okay. So just to recap what we did last time. So I gave you a discussion on. I gave a discussion on how production profiles are typically calculated in a company. You have two departments, and then reservoir engineering, they have their own set of guidelines. They want to check which well placement will be best. They want to check also the recovery factor. They have I think there were some things that we covered last year that I forgot to mention last Friday, but I think there were not that many, so okay. Like for example, they have some guidelines that they want to achieve. Okay, one of them is the recovery factor, where to place the wells to have better recovery factor, how many injectors do I need, where are these injectors going to be located, if I'm doing any EOR, and they are typically what we discussed. They are typically have some assumption of this minimum bottom hole pressure. Okay. And the way Reservoir Simulator works, I have to specify these two numbers, right? Target rate that I wish to produce, and then the minimum bottom hole pressure. If I impose this rate and my pressure is still above that pressure, that means that I will be able to produce it. Okay? If not, then I have to reduce the rate and simply fix the pressure constant, at a constant pressure. And for some cases, some wells can be operated actually at a minimum bottom hole pressure. For example, when you have an electric submersible pump located at the bottom of the well, then you're able to ensure that you are operating always at a relatively constant bottom hole pressure. However, it's not the most general case, so that's why typically they send the profiles and they send the rates, all three phases. Okay, because oil, gas, and water, all of them, they contribute to pressure drop. They send the flowing bottom hole pressure, which will be, in our case, remember, the available pressure at the bottom of the well. Okay, after Reservoir Simulator computes from reservoir pressure all the way to flowing bottom hole pressure. Then comes these guys from production and facilities engineering. They have a production simulator, which is typically steady state. They also use sometimes transient. We're going to talk about it in the flow assurance part. When they want to see a transient phenomena like slugging, or they want to see there will be any accumulation in the pipe. But they verify at each point in time. They go time by time and they verify, are these combinations that I got from reservoir guys, are they going to be feasible? Will I be able to produce them? If not, and have to maybe make some planning of artificial lift if to make them feasible. But if not, ultimately I just send feedback to the reservoir guys, and I simply flag there, for all of these years, or for all of this month, or for all of these dates, you won't be able to produce the rates. Okay. Then I gave some comments. How do we produce profiles? So one of them is a standalone reservoir simulator. Actually, that's one of the preferred options. Then that's becoming more and more popular. I use a reservoir simulator that I say coupled, and we are going to today hopefully to say a few words about what coupled means. But basically, this process I try to make it in the same software. Okay, you see, it involves a lot of communication between that department and this department. It's a time-consuming process. It might take a few weeks. So people try to put everything on the same platform, such that these guys, they have access to that platform. They modify only that part of the model. These guys have access to the same platform, but they modify just the reservoir model, and then they can run them together. Okay, so that's the intention. And this, it's supposed to take care to still compute production profiles, that take care of the reservoir side, but that they fulfill, you will be able to flow them through the wells and network. Other approaches are simply material balance and inflow, which is equivalent to the reservoir, but a much more kind of a simplistic approximation. I make a single tank, a single volume. I don't subdivide. I take away the heterogeneity. I have to use average properties, and then I use an IPR, because material balance simply gives you, if I take out something from this tank, how will the reservoir pressure saturation will change with time. Okay, but doesn't tell you anything about production rates. So for production rates, you need some sort of an IPR equation. That's the approach we will be using in class. Material balance, and then coupled with a well network model, and essentially is more realistic, and we don't have to go to such an extent to use a complicated reservoir model. Okay, which to learn it in this course will be cumbersome if you don't have the background. Okay, so that's why we choose like a midway. We try to use reach a middle point between complexity and also usefulness to teach new concepts. Okay, and then we have very early field development use, at least in Norway, when we use some type curves. We have some wells that I have proposed some particular decline, either by theory or simply by historical data that I have, and then I use some of these wells to make up my production profiles. Okay, but usually if I already have enough data, I try either to populate a reservoir model, or I try to make at least a material balance and IPR. Okay, depending also how big is the reservoir, how big is the team I have, how much data I have available. Okay. Then we went and we were working on this exercise of the Snøhvit as a field located quite north. I'm not sure, I think it's still the farthest north in Norway, I think. Goliath, I think it's a bit south. And there we had, I decided to start with the relatively complex case, realistic case, and then, instead of starting, I think last year I started with a simpler case, and then we started to build up to a more complex case. Okay, this year I decided to go right away to this case. Okay, so we have 9 wells in total. Each one, 3 are arranged in templates of 3. Okay, so you have 3 templates, and then you have each well is identical. They produce the same. You have flow lines connecting the template to the pipeline entry module, which is simply a structure that connects all of these pipes together in a manifold. And then you have the main pipeline, transportation pipeline. This one has 150 kilometers all the way to shore. And we said we have to compute the rate for this configuration. And we already have some plateau rate that has been not agreed, not designed yet, but simply by agreement with customers. Okay, the customer, they want certain amount of gas, and I'm going to deliver that gas. And our intention was, or our main task was, to compute plateau duration and also post-plateau production. Okay, plateau duration we have done, and now today we are going to calculate post-plateau production. Okay, and then I say some other simplifications which are quite okay. Is only dry gas, no liquid, so I'm neglecting condensate, every oil that drops from the gas. I'm neglecting water, again liquid water, fresh water that drops from the gas, and also no chemicals. Usually you will see in flow assurance lecture we have to inject some chemicals to avoid something, to avoid a problem. Typically it can be corrosion, can be scale, can be hydrate. Okay, so we are assuming we are not taking that into account. Okay, and I told you we are going to make like it was like an energy balance, but we have one big, and I'm going to make some comments today about the choke. Okay, the choke model, we decided simply to neglect it. Okay, so that's why we said that's where I'm going to make my equilibrium point. Okay, so we said I'm going to calculate energy or pressure in this case all the way upstream of the choke. I'm going to calculate energy or pressure just downstream of the choke. Yeah, and then I have to compare these two values of pressure. Okay, because I have the choke in between. The choke allows to drop pressure from a high number to a low number. So if that difference is positive between wellhead pressure and template pressure, that means that I will be able to produce the rate. If on the other hand is opposite, the downstream pressure, the template pressure, is higher than the wellhead pressure, that means that I won't be able to produce the rate. Yeah, and I have to reduce it. We will see now that's not the way commercial software works, okay? But it's a very nice way to understand it. But the way software works, it's in a slightly different way, and you have to be aware of it, and you have to be careful. Okay. Okay, then we talk about the equations we are going to use. The dry gas material balance, very simple equation, is implicit, but we got rid of that problem. The C factor, you already know how it looks like. Critical temperature and pressure. The IPR, I told you that's the low pressure. You probably on the exercise you get for home, you have to do it for like medium high pressure, where the equation is slightly different. The tubing equation using the Bernoulli equation and integrating for the change in density. Okay, and the equation looks something like that. Okay, some of the nice things, and I want to here to make a comment about that. First, I have for the let me maybe make it on today's. Okay, some. Okay, so you have there, if you see on the equation, you have T average, okay, and you have Z average. Okay. Okay. T average, if you are talking about a tubing, will be T flowing bottom hole temperature and TWH, okay, wellhead temperature, plus divided by 2. And C average, the same thing. C average will be the deviation factor at flowing bottom hole plus the deviation factor at the wellhead divided by 2. Okay, so that means that I need to have some temperature estimate beforehand. Okay, either I measure or either I make an assumption, because I'm not solving in this equation the energy equation. Okay, so just be aware here that an estimate of TWH is needed. An estimate, an assumption, and that's going to affect, remember, that's the C, okay, that we, all of this becomes the C in my equation, okay, to compute C, to compute CT. Another thing I want to call your attention to also, it's so all the rest is relatively constant. The tubing diameter, pressure, the S, okay, has the same complexities. The other thing that is also worth noting is the friction factor, FM, okay, the Moody friction factor. Okay, that's the friction factor. And if you remember, friction factor is a function of what? Okay, or how does it look like? It's a function of what do I typically plot here? It's just trying to wake you up, okay? I'm already warming up, so just trying to wake you up. Okay, Reynolds number. And Reynolds number is V diameter, okay, by me. In our case, we are using D for diameter, so okay, and it's a function of something else, right? If we have the laminar regime, looks something like that, 64 over Reynolds, right? We have some ugly thing that we don't know exactly what happens, and then we have a series of families of a family of curves, right? And what are these curves a function of?
Velocity.
Velocity? No. So it's a property of the pipe. Okay. This is going way back to your when you took this course the first time. Okay. We have something called relative roughness, right? And that is the roughness divided by D. And that means if I have my pipe, typically have some roughness, okay, that I simply measure that value, okay, that E, okay, simply the roughness. I think they used sandpaper by that time. They glued sandpaper to the wall of the pipe. Okay, so you see that first, well, why the friction factor remains constant in that case? Because really it's a function of Reynolds, so it should be a function of the velocity is a function of Q, right? And Q depends on density. That's local, okay? Q local. And Q local is a function of density. And density is a function of pressure for gas. So it's changing. It should be changing along the pipe. Okay? The thing is that for gas, first, velocities are very high, okay, compared to liquid. What can be like a typical liquid velocity on a pipe? On a kind of a well or a pipeline? Okay, for example, for liquid, okay, let's say here liquid or oil, we are saying velocities maybe someplace between 0.5 and maybe it's between 4 meters per second. Okay? When we talk about gas, it can be much higher. Okay, the gas could be, I don't know, from maybe 5, but all the way maybe it can go even to 40. Okay, or 50. Okay, so it's an order of magnitude bigger. Okay, so that's one of the advantages we have with gas. Okay, density is low, that's true, okay, compared to liquid. But the viscosity of the gas is very small, okay, it's much smaller compared to viscosity of the liquid. Okay, therefore the Reynolds number of the gas is very, very big. Okay, is very, very high. So that means that you will always be in this range, in the fully turbulent regime. Okay, and in the fully turbulent regime, it's not a function of velocity anymore, but it's only a function of this roughness, right? The relative roughness. So there, the friction factor is only a function of this epsilon. Okay. And then also, that was done, I think, in the 50s. People saw that the roughness actually is a function of the diameter. Okay, if you use a big pipe, then you will have some roughness. If you use a small pipe, then you will have another roughness, simply due to manufacturing, okay, to fabrication. So because of that, that was, I forgot the name, but it's on in the compendium. However, is epsilon, or E is a function of D. Okay, due to manufacturing. Okay, so they went, I think were two guys, they went around to different mills, I think it was in the US. So they went around asking around, and finally they came up with that relationship between friction factor, between epsilon and D. Okay, and finally they use, that means that Reynolds, that friction factor is only a function of D, okay, for gas. Because you're in the fully turbulent regime, okay, so you're only a function of roughness, and then roughness is only a function of diameter due to manufacture. Okay, let me show you the expression. I think it's in the compendium. I don't trust that you will search for it, maybe some of you. Well, you will probably search for it, but a bit later when it gets close to the exam, right? I guess. Okay. Friction factor, it was, I think, Smith. Okay, to say friction factor is only a function of diameter, and that's essentially because the roughness of the pipe is just a function of diameter, simply by manufacturing. Okay, all the mills always have more or less the same, the same roughness. Okay, and it's that expression here, 0.077 d over. Okay, so just that comment that these are some approximations you have to be aware when using this equation. Okay, the tubing, dry gas tubing equation. Average, I have to assume a temperature, and also the friction factor I'm assuming is always in this range, which for gas is like a good approximation. Okay. Okay, so let's go to our exercise. We have still, okay, so we said horizontal pipe, we use the same tubing equation, but simply we have to get rid of this, the height difference, okay, the hydrostatic part. So for that I have to apply the limit when S is 0. And that we have to do it with this L'Hopital. And that was our approach. We have to go from reservoir to wellhead, and from separator to template. One is co-current, we go with the flow, we calculate the available pressure, and one is counter-current, we go against the flow and we calculate the required pressure. Okay? This is the required pressure to flow this rate against this pressure, and this is the available pressure that I get after I flow from here with that particular rate. Okay, so that's why I call it available. One, I'm going with the flow, simply seeing how much I have left. Okay, and the other is required, because I go back, I don't have that energy, but I just want to see how much will I need to flow against that pressure. Okay, then we talk very quickly about integration. We are going to assume simply the rate is constant throughout the step, and yeah, and we just had a short discussion on BBA. Okay, that how we are using here all of our BBA functions. Okay, so now we are ready to continue on our exercise. Okay, so that's the result, I think. Let's see the tubing coefficient, because we changed that last time, but I think that was the original coefficient. And we have here positive. I'm able to produce the rate, delta P choke, write positive, positive, positive until it becomes negative. Okay, so that means end of plateau. And Jesus wrote here beginning of compression. Okay, when I'm not able to deliver the rate anymore, I want to add energy. In our case, simply we say open choke. Okay, and the decline will start. So how do I calculate now? What do I have to do now here in this -2? Okay, the energy I have is not sufficient to flow against separator. Okay. So,
Open the choke.
okay, when the choke is open, what happens with wellhead pressure and template pressure?
Less pressure
Equalize.
to close.
They are, let's say, they are physically, they are in different places, right? If we look at again our, okay, physically one is here and one is here, but that is really not much distance in between. There are a few meters. Okay, so if the choke is open, this component is open, 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 then the two pressures should be essentially very close, should be the same. Okay, and that is equivalent to say, to not make any change in my, because now I could say, well, now this pressure is equal to that pressure, okay, somehow here in my Excel sheet. But I don't want to spoil the equations. I don't want to start, you know, messing with my layout. Okay, so I'm going to say, if this one becomes 0, that means that is open choke. Okay, so how do I make this guy become 0?
Improved oil recovery.
Hmm?
We'll have to submerge the pump or.
Yeah, but if I don't have any, I cannot add any external energy. Okay, simply less rate. Yeah, do you see that? Why less rate? Okay, what? So now we were using some rate to go from here to here and here to here, right? Okay, what happens if we use a lower rate?
Pressure drop will be in the
Yeah. So the available pressure that I have here will be lower, right? Because I have less pressure drop here and less pressure drop here. Do you agree or not? Let's make it as a plot, okay? So if let's make again our well system. PR, PWF, and P wellhead. So if I take only that system, QG, and I want to make a plot of PWH versus QG, and this is Q of the well, right? We know already for 20, right, for a given time, okay, we have 20, what was the well rate that we had? Okay, let's go exactly to this time 21. For 20, we have a pressure of, wellhead pressure of 79, okay, 80. And the well rate is 2.2. Okay, so it will be 2.2. This will be 10 to the 6. And we know this guy will be 80. Okay, and this scale, it's in bar. Axis is in bar. Yes? That's what we have at time. Let's say here at time, and this is 21 years, I think. Yeah, 21 years. So no, it should be actually 22. We should be here. Yeah, 21. At time 21 years. Okay, so that means at end of year 21. Now at that particular time, okay, let's say we're looking at that particular time, that means that reservoir pressure is constant. Okay, reservoir pressure is 115. Okay, reservoir pressure Now I ask you, what happens if I increase the rate? Okay, well, what will happen with that pressure that I have here? Okay, it should it be, let's say I use now 2.5. Okay, should it be here or should it be here? Lower. Okay, why?
Because we'll have more pressure drop in the tube.
Okay, like Alpita, she is arguing that you have like the rate is higher, right? And then you have more friction. The hydrostatic pressure will be the same as the previous case, right? But when you have a higher rate, then simply you have more friction losses. Is that, all of you agree? Yes? Okay. So yeah, in reality it looks like that, and the curve looks something like this. Okay? Passing through much nicer. Okay. Now, what happens with, let's try now to make the same exercise. I don't want to confuse you, but let's try to make it on the same plot, okay, of P template. Okay, P template, remember, we are now looking at, we have flow line, and then we have the P plem, and then we have separator, and then we have P template, okay? And now we are going from here to here, we are going from here to here, okay? And if you see, how is that pressure? Let's go template, require, and it's constant, okay, throughout the time. That's not what happens with PWH, okay? PWH is reduced with time. And it's reduced with time because reservoir pressure is also reducing with time, right? So we are starting from a different point in every time, okay? While this one, 82, is always starting from the same fixed pressure, which is separator pressure. With no matter which time we are, it's always going to be 30, okay? So let's see. That rate, okay, here it's a bit confusing, that system, because we have here a field rate and here we have a template rate. So it's like a strange, you cannot make a plot exactly like this, okay? But you know that in our case, right, Q field is equal to 3 times Q template is equal to 9 times Q of the well, okay? So all of them are proportional. So when I say 2.2 rate well rate, that means 20 million field rate. Okay? So I can, that's why I can plot it on the same plot. Okay, that's why I can use the same scale. Okay? So let's see here now. This will be also P template. And we know we have 82 for 2.2. Okay, so let's say that is 82. Okay, so now I ask you exactly the same question as with the PWH. How will P template change if you go to the right or if you go to the left? If you increase a bit the rate or if you decrease the rate? Okay, here I'm looking at this system, right? Before I was looking at this system where the flow is going with me. Okay, I'm going with the flow against me.
If you decrease the rate, the template pressure will drop because friction factor.
Okay, yes. All of you see that? Right? Because if I use, here I have some pressure, fixed pressure, okay? If I have no rate, what I will have here on 0, when the rate of the well or the rate of the field is 0, what pressure I'm going to get here? Simply separator pressure, right? Because we are assuming the line is horizontal. So if I have no flow rate, simply have balance of pressure, right? So simply I should have here 30. Okay, so we have the starting point. Now when I want to produce not 0 but a little bit, okay, then I will need to overcome all the pressure losses in these two pipes, right? So then the pressure should be higher. Okay, so the pressure will do something like this, increasing, 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 okay, and you will have a curve that looks like that. Okay? Now, okay. So it's a bit of a strange exercise, okay, but you will see a bit where I'm going. What we have done so far, 4 times 21, right? We came here and we calculate that pressure, and we see what will happen if we increase or decrease the rate, okay? And also for the same time, but actually we know this is valid for all times because it doesn't change. We also came here and said this pressure, what will happen if I increase or decrease the rate? And we got the blue curve, okay? Now I'm asking, if there is no choke, okay, how should these two pressures be? And you gave me the answer before. Equal, right? So that means that the only point where this system, if I put them together, where it will be able to operate, it will be exactly here, right? Which is a bit below 2.2, okay? Which tells you I have to reduce the rate of the field. The rate should produce now less, which is also consistent with what we have been discussing so far. After plateau, we're starting to entering into decline, okay? But now you see why, because we have these two curves and they intersect, and that gives you the equilibrium point, okay? That is the equilibrium point. That clear? More or less? Okay. Now, what happens, I ask you, what happened when reservoir pressure was bigger? Okay, when we were, for example, year 20. What happened there? Which one of these, what changed? Okay. You say, I will say that the red curve changed, right? The red curve will be different, but the blue one is always the same. Okay, so the red one, let's go to another year, for example. Let's go to year 10. Okay, we have exactly the same rate, but now the pressure we have is 165. Okay, so let's see, 2.2, and we have 165. So 165 will be like twice, will be here. Okay, and you have exactly the same thing. I increase the rate or I decrease the rate. Let's use another color. It will be something like this. Okay, so you see that that curve of the available pressure is actually shrinking when reservoir pressure goes down. Okay, and if I want to produce that rate, okay, then these 2 points at this particular time, this curve, let's call here at time 10 years, okay, the pressure is not the same. The blue one is upstream the choke and one is downstream the choke, and the choke is in between. So these two pressures don't have to be the same, okay, but the choke has to bridge this pressure difference. Okay, the choke has to, that is the delta P of the choke. Let's use another color. Okay, this guy here is the delta P of the choke. Okay, and you see the delta P of the choke when this curve is becoming smaller and smaller. Okay, it's actually also becoming smaller and smaller. Okay, so I always choose a delta P of the choke to bridge this difference until I reach to this point when they are both equal. That happened between the year 20 and 21. Okay, and after that, simply have to move on this intersection. This will be becoming smaller and smaller, and I'm moving on this curve, moving on that line. Okay. That clear? More or less? Okay, so let's take a break, 15 minutes, and we come back, we try to apply this to our exercise, okay, to calculate the post-plateau decline. Okay, so the way we are going to do that on our Excel sheet, right, to find the equilibrium rate, everything in this sheet is a function of this rate, right? Everything on this line. And there are some things that are function of the previous time, but essentially all the pressures that I have, available pressure, required pressure, they're a function of this cell. Okay, so I will change that cell. Let's first manually, just to see it, 19 million now, e to the 6. And you see now it's positive, so it should be something between 19 and 20. The way we have done it in the past is we tell Excel to do it automatically for us, and there are two ways to do that. You can do it in data, what if analysis, goal seek, yeah, still works, goal seek, and here we say which cell do we want to change. Will be this one. Okay, we want to change it to 0, and we want to do that by changing this cell here. Okay, and sometimes now it was successful. The rate has to be lowered to 19.6 in year 21. Okay, and then we have to repeat now for year after. It helps that you use a number similar to this one, so I will copy and paste this value. Okay, and now I will use again this this cell, drive it to 0 by changing this cell. Okay, so now the rate went to 18. Let's try it for the last 3 years. Remember, up down to which rate do we have to take down the rate? What was the abandonment rate, if you remember? 5. Okay, 5 million. So still we have quite a few rows to go. So then you're left with some homework. Okay, the 16 starts dropping quite sharply. Then let's see this one. Why? So one thing is, if you cannot, I don't think it works if you simply, because this cell now has a formula. Okay, so Excel doesn't know that it can change it. It knows that it has to be always taking the value of another cell. Okay, so if I say I think it won't work, if I click here, say to value 0, and then I change here. Okay, cell must contain a value. Okay, now he says now you're linking to something else, so I cannot change that constraint. So the way to do it, you see that plateau ended here, and then the rest it was simply a number, a value. Okay, so then that's why, and I give this initial value, then again I solve it to 0, then okay, and then the last one, the same thing. Okay, so let me see, I think I have some, oh no. So in this period, we are here, remember, we are not able to produce 20 exactly. Okay, so when we are in year 20 and 21, was, you know, the discussion we had earlier. Okay, we have Q of the field, and we have time, okay, and we had a very long period, exactly what we needed, which was 20 years. Okay, but then at year 21 we got 19.6, okay, which is slightly less. It will be here, but what we are approximating, instead of using a trapezoidal integration, we are approximating simply constant for the previous step. Okay, and here we will assume constant for that step, and here we found 18, I think. 18.2. Okay, so this number will be 18.2. This was okay, so we are approximating actually this decline by that decline by a series of steps, a series of rectangles, which will be, you see, all of this is overestimating the value of the cumulative production. Okay, so you're kind of consistently overestimating production. Okay, I will try to see for Friday if there is a way, instead of you have to do it manually, there is a way to program that in VBA. Okay, in VBA you can not only have functions, but you can also make a script, a series of instructions that you want to execute. Okay, so in that case I want to, for each time I come here and they say use the goal seek to send that number to 0 by changing this number. Okay, and that's very useful if you want to apply it for the rest of the cells. So I don't think I want to do it here. We will kind of spend some time, but I will try to have it ready for next class. Okay, and then that will be something that will save you some time. And then it's a nice opportunity to talk about scripts, okay, which we use in okay. Then we will use in the future this exercise. I think we are going to have an exercise set that you have to expand, do some more tests on this Excel sheet, on this exercise. But we have, for the future, they are planning not to reduce production, but to use a compressor. So here you have to evaluate compressor, how much longer plateau you can get with compression. And also you have here NPV calculations of the project, okay, to calculate NPV. So we just don't discard this sheet, just keep it there someplace, and we will use it for later lectures. Okay, also try, here I'm doing myself, I hope some of you are following, but just try to watch the video again and just do it by yourself, okay, such that you have it ready, feel like I have done. So I want to say a few comments here. So in reality, the well plus network solver or simulator works differently. Okay, you have to do some tricks, or it's not very straightforward simply to impose a rate, okay, like what we have done here. They work in a slightly different way, okay? They work differently. They work has a solver of system of equations, okay? Okay, and what do I say by that? If we look at the equations we have, okay, like in this case, for example, that's one example for dry gas, but we will see later how it's actually computed inside the simulator. But you have how many equations? You have IPR, right? So you have QG, CR, PR squared, PWF squared to the power of n. Then you had TPR, that you have QG is CT PWF squared e to the s minus P wellhead. Then you had the pipeline or flow line, right? QG, C flow line, P template squared minus P plem squared 0.5, and then you had the pipeline, which was the QG C PL P plem minus P separator 0.5. Okay, so let's count equations that we have and unknowns that we have. Okay, so you have, in the first one you have, let's make a tally with equations. Then we have unknowns. Okay, so here we have one equation. How many unknowns we have? Essentially will be rate and PWF, right? So these two. Okay, so I have two unknowns. Now I have two equations, and how many unknowns I have here? So actually I have these two are the same as before, PWF and Q, but the new one I have is PWH, right? So now I have three. So I'm catching up. Then I have, so let me just mark it here, question mark, question mark, question mark. Here also question mark, question mark, question mark. So I have two more unknowns. So I have 5 here and I have 3 equations, right? And then finally I have question mark, question mark. So I have 4 equations and 6 unknowns, right? You have to do QC. You know, I might be doing a mistake. Here is Q and PWF, Q, PWF and PWH3. Here Q is the same as before. These two are new, so I have 5. And then you have Q is the same as before, and P plem, no, sorry, here should be 5 also, right? Because P plem we also had it from before. Okay, we have it in this equation. Okay, so we have 4 equations and 5 unknowns. We cannot solve. Okay, is underdefined. Okay, so we need that famous equation of the choke. Okay, which tells me QG has a function, and we are going to see now how it looks like, of P first P wellhead, P template, and also of the opening. Okay, opening. Okay, so here I have 5 equations and I have exactly 5 unknowns if opening is given. Okay, if I give the opening 30%, 50%, 100%, then it will be fully defined. Okay? Yes? So basically what we are trying to make in a commercial simulator, that's actually what's happening. You have all of these equations that have to be solved simultaneously, and then you have to, so let's make it like okay, so let's make it like a big box. Okay, we have some input. That input that we have is a PR, for example, right? We don't need anything else, I think. Then we have the opening, choke opening. Okay, so let me erase that. We only have pressure, choke opening, and here we have the system parameters, okay, which are CT, S, NCR. We have C, PL, CFL. Okay, we have all of these system parameters that I'm supposed to know beforehand. And at the end, what do I find? I find all the collection of, first I find the rate, which is what I'm really looking for. Okay, and here we should be, this is of the well, right? This is of the well. Yeah, I messed up a bit. We need a few, sorry, before doing that, we need, because the rates are different. Okay, so this is Q of the well, this is Q of the template, and this is Q of the field. Okay? And we have a series of additional equations that tell me Q of the well is Q of the field divided by number of wells, and Q of the template okay, sorry for the screw up, Q of gas of the well is equal to Q of the field divided by number of templates. Okay, and here you have 7 equations, and I have 2 more unknowns because they are the rates of the field, the rate of the template. So here I should have let's maybe do it again. Okay, here we have, these are the same, so here we'll have 1, 2, 3. Here we have 4, 5, 6. Seven, okay, with the field, and here I think doesn't change, so here you have 7, 7, and 7. Okay, because we forgot to say that the rates are not equal, but we have a relationship between the rates. Okay, how much each one produces. Okay, so that gives you 7. Okay, but I'm saying that you can think of that as a function. Okay, that's a well plus network model where you provide all of that input, system input. Also, you should give number of wells, number of templates. You provide reservoir pressure, you provide the opening, and then you calculate, solve that system of equations in an efficient way, like Newton-Raphson, and then finally you end up with Q of the well, of the field, Q of the template. You obtain PWF, PWH, P template, P plem. Okay, you obtain all of those. So now, what happens if I want to operate in plateau mode using this model? Okay, what do I have to impose? Or what do I have to find? What do I have to solve for? If I want it to be in plateau, right, I want the Q field to be exactly a number. Let me put it, so it becomes a constraint, what we call a constraint, okay, that maybe let me put it on a different page. Let's call this system parameters. Okay, that's input from Reservoir Simulator. Okay, and that's the output. Okay, and that is what I call the adjustable variables. Just to tell you that in the simulator is slightly different, and it's quite, if you don't understand the terminology, it can be a bit difficult to grasp, okay, because it's not so simple like what we have done before. Okay, so you have a constraint. Let's put it here. The constraint is that the Q of the field, okay, the QG of the field should be equal to Q, a desired Q plateau. Okay? So you have to put a solver on top of this model already that you have, saying change opening. Okay? You make it here, down here. Okay? It will change this value, okay? Change the opening and read this Q of the field. Okay? And that's a solver. Okay? Such that it will, for example, use 30%, see how much rate you have, see if it's equal to your plateau. The plateau should be here actually. Okay, and that's an input to this solver. Okay. It will use an opening, see what is the rate that you find, okay, and then compare. Is it equal to my constraint? Not. Then I find a new opening, and then I run again my network model, and then I read again the plateau. Okay, so you need some. It's like 2 iteration loops. Okay, here you are. It's a network solver or it's an equation solver. Okay, and this simply is another solver. Okay, that's the choke opening solver. Okay, you see you have two stages. So for each run, you see that I'm changing opening, running the network or running the system of equations and finding a new rate. Is it equal to plateau? And then I iterate. Okay? Confusing, but it's essentially equivalent to what we are doing without any iteration. Okay? If you have the choke model. Okay, let me show you how the choke equation, for example, looks like. Choke equation, choke. Okay, I have it in the compendium, which I closed. Okay, looks something like that. Okay, for example, for dry gas, and here we have it's in page, the whole derivation. If you want to see it, you're bored one day, it's on page 166 of the compendium. Okay, so on this Y, it's the pressure ratio between P2 and P1. P1 is the pressure upstream the choke, and P2 is the pressure downstream the choke. And the choke here is modeled, usually most choke models are modeled like that. Okay, you have like a big restriction, okay, and then you have an expansion, and the fluid here you have a contraction, you burn all the energy, and then you have some expansion, the fluid coming out. This is the area that you call 1, area 1, and this is the area that you call area 2. Okay, and if you plot pressure across this choke, pressure along X, okay, you'll see that pressure essentially here is very high, and then when you reach, you have a very big drop. and then it starts to recover, but not that much. Okay, typically something like that. So you have P1, that will be P1, and that will be very close to P2. Okay, because you have some recovery of pressure, but not really that much. Okay, because that's the intention of the choke, simply to drop the pressure. Okay, so that equation usually works if you have, so if this y, it's okay, is above the critical, okay, something that I call the critical ratio, that is something between that number is something between 0.6 or 0.5. Okay, that means that the pressure downstream is less than 2 times, or is half the pressure at the inlet, okay, of the choke. If that happens, then there is okay, there will be critical flow, and you know, at critical flow, the pressure, if there is any pressure change here, normally it travels with the speed of sound all the way here. Okay, that means that for some reason you have slugging or you have variations of pressure down here. Okay, they propagate with the velocity of sound, and they also, you have them here. Okay, so they will propagate upstream all through the system. But if you have critical flow, then the velocity of the fluid starts being very close to the velocity of sound. Okay, so any wave, any variation that I have in pressure here simply won't pass through the choke. Okay, you won't see anything upstream. Okay, so the equation of choke is if y is greater than yc, okay, then qg will be qg critical. Okay, will be that equation that I have here. Okay, that equation that I have here, but with y equal to yc. Okay, every place where I have y, I have to substitute this y critical. Okay, however, if y is less than the y critical, then simply have to use this equation. Okay, and graphically, if I see, maybe the equation don't mean much to you, okay, but I want to plot delta P of the choke versus QG, okay, with P1 constant. This equation here is essentially like a nonlinear function starting as this equation. Let's call it here in red. Okay, this equation will be this part here. Okay, and after I reach that critical point here, I reach this y equal yc, then simply it becomes this equation in blue. Okay, that simply is a constant. Okay, so that's the choke equation. I have, whenever I try to circulate more and more rate, okay, I get a bigger and bigger pressure drop. But at some point, actually, I reach this critical condition in the throat. So it doesn't matter, I cannot go higher than that velocity, or I cannot go higher than that mass flow rate. Simply, I'm choked. Here I'm reached critical conditions at the throat. Okay? So those are the two equations that are used, for example, for dry gas choke. And they are actually, you have to know this critical ratio, and you are using one or the other depending on where you are. Okay? So you see why I didn't want to include them. Okay, I'm just showing them here such that you know that they exist, so you know how they look like, but actually it's quite challenging, especially this square root here and these exponents that I have. It makes it quite challenging for solving, okay, to include it in the system of equations. So basically we took that complexity away, simply say that if it's positive, then you are able to flow. Okay, you don't care about this equation. Okay, that equation is not that, is not that accurate. Okay, but just wanted to show you, like, in a commercial simulator, probably that equation, ugly equation, and many other equations of the same shape will be included here. Okay, which makes it very challenging for the solving process. Okay, so here we have that's inlet pressure, standard conditions, pressure and temperature. In Norway it's how much is that in Norway? P standard condition is 1.01, 325 bar. T standard conditions is 15.56 degrees Celsius. Brazil they use 20. Africa they use some other numbers, okay, but it's like a reference. Deviation factor inlet, temperature at the inlet, molecular weight, that is, this R is universal gas constant divided by the molecular weight of the gas. And K, what is K? K is the ratio between specific heats, right, which is Cp divided by Cv. Okay? We are not going to talk too much about choke. We don't care about choke. We actually can do our calculations without looking at the choke equation. But I just want you to be aware, when you go to a commercial software, they have these equations programmed inside, and they chose all the choke models that you have, all people that have proposed different models. So that's the complexity. That's what you're trying to do here. You include that equation, which is actually in two parts. Okay, you have two sections, because that behavior cannot continue forever. It's not that you can increase the rate as much as you want. At some point you reach critical flow in the throat, and then yours done. You cannot go higher than that rate, no matter what delta P you put across. Okay, simply because, let's say you lower the pressure here, right, you get more rate. Let's keep this pressure fixed. Lower the pressure here, the delta P will be bigger, right, and then you get more rate. Then lower the pressure once more, then you get more rate. But at some point you will have critical flow here, so then any change you make here, it won't be noticed by this pressure here. Okay, simply you lower it, and here is choked. Simply you cannot get any more than that. Okay, at that point is where this happens, and then the rate simply flattens out. No matter how much I reduce P2, okay, no matter how big I make the delta P, I will always have the same rate. That's a critical QG critical. Okay, that is choked. We call it flow is choked, okay, or we call it critical flow. Okay, so I need to have these two equations with that if here, depending on the delta P, and then I have to solve the system of equations, and then I also have to give a choke opening. So where is the opening in this equation here? How I represent the opening? A2, right? This throat, actually. If I can change that either by putting a smaller choke, that's what I do in onshore, right? I simply come, I unscrew the choke, and I put another insert with a smaller or bigger throat, okay, which I call it in 1/64 of an inch. Okay, so in onshore fields, let's make that comment. Okay. Bean chokes is called bean choke are often used. Okay, where I change simply a bigger choke will be like that. Smaller choke will be like that. An even smaller choke will be like that, but I have to go and change it. So if I want to achieve my plateau, I have to go every 2 weeks or every month or every 6 months. I have to go and change, close the well, I have to shut in the well, and I have to change the choke, change the insert, and change the for a smaller one. Okay, and this is typically given in 1/64th of an inch. Okay. When we are offshore, we cannot send someone, especially if we have, it will be simply is too much. It will be too much work. Okay, so they use adjustable choke. Often, adjustable chokes are used. Okay, where I can simply regulate somehow that throat. Okay, that's a type of choke that is called a needle. Okay, that's called a needle choke. It's not used very much. Okay, but you see, you change here. You have your A1, and then you have your A2 at the throat, which will be that short distance. That will be your A2. Okay, and by moving the stem up and down, you're regulating your A2, your area of the throat. So this will be adjustable throat. Okay, so that's what I changed. When I change my equations, the opening, that is A2. That is the opening. Okay, and I can make it smaller, bigger, whatever I need. Good? Okay, so I think we keep it for now for today. That's all for today, I think. We had a recap of what we have done last class. I think that was necessary to put us all in the same page. A few comments about the tubing equation. We need to have temperatures, and because it's gas, okay, only because it's gas, we assume it's always fully turbulent, and we assume that friction factor is a function of roughness only. Then we said, what happens when delta P of the choke becomes negative? In our case, simply we have to keep it open and we have to reduce the rate. That means that the energy at these 2 points have to be equal, the pressure. They are now in the same point. When the choke is open, wellhead pressure and template pressure, they are equal. Okay? Then we did the calculation. We used Goldsick, and there is also something else called solver that we will use later. And I told you in commercial simulator works a bit different. Actually, you are solving a system of equations, okay? And there you can have temperature, you can have other things there, and you see that I have to make a count how many equations I have, how many unknowns I have, and then see if they are equal. Okay. At the end, I make the sum, and this guy to the left should be equal to the guy on the right. And then I told you to visualize it has a box, we have a function, and then you simply give PR from Reservoir Simulator, you give your system parameters, and you give your choke opening, and it computes for you all of these things. Okay, the rate in each well, the rate in the flow line, the rate in the pipeline, and all of these pressures. And then I say, if using this model you want to produce in plateau rate, you have to put another solver. And this solver is usually sometimes called optimizer. Okay, so this is sometimes, and it's not sometimes called optimizer. Okay, so I say I give a constraint, the Q of the field has to be equal to plateau, then the solver is going to change the opening, run the model, read the result, and see if it's equal or not. If it's equal, it stops. If it's not equal, tries a new opening, and the system is repeated again. Okay? It's called optimizer because if you don't have that constraint, okay, you can simply say I want to produce as much as gas as possible. Okay? And in that case, what it will do, it will simply try to open the choke at the fullest. Okay? And then we talked about the choke equation, what we are not covering in this course, simply to tell you how ugly it is, how difficult to converge it is. It might be inaccurate, that's why we include that tuning factor here, that's tuning parameter. Okay, they call it calibration parameter. And we have two equations basically, one if it's critical and one if it's subcritical. Okay, and I show you like graphically how the equation looks like. Okay, any question before we close? No? Okay, see you on Friday. Have a nice week.